I'm going to show you the proof that Isaac Newton did when he made his formula of G m1 m2 over d squared, and he asserted that this d is the distance from the geometric center of mass of each body. So this is called the shell proof. And what we're going to do is we're going to assume that we have just a shell with no mass in the middle. And we're going to prove that even with just a shell, you take the distance from the center. Okay? So we're going to split the shell up into little rings. Okay? So here we go. So once again, from our definition of potential energy, U equals negative G M mi, that's our little ring that we're going to take, over S. And this is our S distance. Okay? All right, so I'm going to take the derivative of each side. Du equals negative G M dm over S. And similarly, when we were doing the moment of inertia integrals, a dm is a problem. So since this is an infinitely thin ring, we don't have a volume, we have an area. So dm is going to be equal to mass over area times dA. All right, dm is going to be equal to mass, and then our ring is going to be 2 pi r times the thickness, right? R is going to be, this big R is the radius of the sphere. So if I make my ring here, R is going to be R sine phi. So this is going to be 2 pi R sine phi, and then the thickness is simply the arc length, which we learned was R, and then times the change in angle, times R d phi. This is phi, that angle right there. And the area is going to be equal to 4 pi r squared. Okay, everybody with me? All right, dm equals m over 2 times sine phi d phi. Okay, so now we have du equals g m over 2 times the integral of sine phi d phi. All right. Next step is to do some geometry. So little r goes from point P to the center of the sphere. And S goes from point P to our mass in question, to dm. Okay? So S squared equals it's this distance squared plus that distance squared. So it's going to be r minus r cos phi quantity squared. This is r cos phi, we want that distance, plus r sine phi squared. All right, and that's going to be S squared equals r squared minus 2r cos phi plus r squared cos squared phi plus r squared sine squared phi. This term right here, that goes to r squared, because I've got a cos squared plus a sine squared. So that just goes to r squared. So S squared equals little r squared minus 2r cos phi plus big R squared. Everybody with me so far? Okay, great. Now I'm going to take the derivative of both sides. So this is going to be 2s ds. That's the derivative of that is 0. Derivative of that is 0. And then equals cos, the derivative of cos is going to be a negative sign, so this is going to be 2r sine phi d phi. get the derivative of both sides. All right, I'm interested in this term right here because it's in my integral. So I'm going to divide both sides by 2RR. So let's do that. 2RR, and then 2RR. So I'm going to get S ds over RR equals sine phi d phi. There, right there. I'm going to go back there and pop that in there. Okay. So now we have, oh, sorry, this should be U, not du. There. U equals G big M little m over 2 times little r big R, and then S, let's see, times the integral of ds, and my limits of integration are going to be from here to here. From here to here, right? And that's going to be, this is r, little r goes from P to the center. So up here is going to be r minus big R, right? And right here is going to be r, little r plus big R. So this is going to be r plus r, and that's going to be r minus r. All right, so U equals, I'm sorry, I forgot my negative, and my negative here. So many details. Okay, negative G, big M, little m, 2RR, and then times R plus R minus R minus R, and this, as it turns out, is 2R, 2 big R. So, I come back and my potential energy is equal to negative G, big M, little m, over R. And there is your shell.